Looks good from your side? All right, then we will just get started here and keep going. So if there are issues with the stream, let me know, put something in the chat. I will do my best to try to fix it. And hopefully we have fewer mistakes than the last go around. Last semester or last year, I kind of did one of these on a whim. I didn't really double check many of the solutions, so I apologize for errors there. But hopefully this semester we'll have fewer of those. So this is the first in a series where we're going to be going through math, and then I think next week we'll be on to statics, structural design, and a few different topics here. So pretty excited to do this. We'll probably have between 12 and 14 videos when we're all said and done. Each one will probably be about an hour long or so, and hopefully you found the review problems as well that we're going to go over. If you've gone over through some of those, hopefully that helps as well. But if not, you can take a look in the description below. It'll tell you how to get access. So we're just going to jump in, and what I do kind of with each of these problem sets is I start out by saying, okay, well, what is actually on the test? So I went and took from the civil exam specs right from NCEES. There's a link at the top of the page, what's on math. So there's analytic geometry, single variable calculus, vector operations, and statistics. And this is actually a little bit pared down from what it used to be. I've talked to a couple people that have taken the test in more recent times, more in the past year or so. They said they don't remember differential equations, so I didn't put those on here. But we are going to go over some basic calculus and basic geometry, and hopefully we'll get into that as well. Engineering economics, Matthew, I just saw your comment there. We will try to be hitting those later on in the semester, but in the beginning of the semester, I'm gonna focus on some of the more real core concepts, because math is like one of those things that if you don't know how to do it, it makes the rest of the review harder. Statics in another one of those, and then towards the end of the semester I'll throw in like dynamics, I'll throw in the engineering economics, the ethics piece, but I'm going to put those towards the end as opposed to in the way that the NCEES kind of has it in the spec right up at the beginning. But just to sort of focus where we're studying and help you with that. So what we're going to do is we're just going to jump in and try to solve some of these problems. So if you have the problems, feel free to try to solve them. Don't spoil it. Don't tell everybody what the answer is, or maybe where I got something wrong. But we're just going to start in with some basic kind of things, and then so this is what I'm trying to do, some just basic fundamentals here. And obviously I don't have an inside scoop on what NCEES exactly is going to tell you to do or tell you that's going to be on the exam. However, I kind of have been looking at some of the basic concepts, the basic ideas, and talking with different people, having these questions reviewed by some people that have recently taken the test. They said, yeah, this kind of covers the basics. So as we get started, there's some basic formulas, and even this first question, right? We're given a couple things. We're given a slope and we're given a point. So right there, when you think of lines, right, my initial thought is y equals mx plus b. But when you see this also, maybe you're not as familiar with the point slope formula, but y minus y1 equals m times x minus x1, right? So these are two formulas of a line, right? So these are formulas for a line, right? And honestly, so much of what we do is just a formula of a line, and that's one of those things where you kind of have to know proportional relationships and formulas here. Mx plus b isn't exactly proportional, but it's a direct relationship with a constant. Okay, so once we have that, we can also put in here, well, we know our x, we know our y, we know our slope, and we can just really plug in. So what I'm going to do is I'm going to say y minus y1. Y1 is going to be 3 equals the slope here, 12 over 5 times x minus x1. So x1 is going to be 5 as well. So we can multiply this through, and we're going to get y minus 3 equals what? Well, 12 fifths x minus 5 times our 12 fifths. The 5's cancel out, and we're going to get minus 12. So our formula is going to come down to 12 fifths x. We add 3 to both sides, minus 9. Okay, and now we get a formula, and that doesn't actually answer our question, because we want to know that what this passes through, and it passes through all these points except for one of them. And you could break this problem down a few different ways. There are some problem solving techniques and strategies, right? But if you understand slope, what you understand is that the slope here is going to be delta y over delta x, right? So the change in y is going to be a constant 12, right? So we could look at this a couple ways. I mean, yeah, I showed this formula, but when we look at this point 5, 3, we're going to be going up 12 every time. So from 3, we're going to go to 15. We're going to go to 27. We're going to go down 12 every time. So 3 minus 12 gets us to, good grief, I'm not going to trust myself on that one. But 3 minus 12 gets to minus 9. And if we subtract another 12, what do we get to? We get to minus 21. So right away, I mean, we didn't need to do our point slope formula here. I wanted to introduce it just with a thought that, this does work and you are able to make it work. So, however, what we see real quickly is the outlier here is going to be our b value, and that's going to be the answer to this question. That point does not lie directly on the line. The other thing that I wanted to do with this question was I just wanted to introduce a little bit of an idea of how to use the calculator. So I'm going to bring up my calculator here, and one of the things that you can do here is in the calculator, I like to use the TI-36X Pro, so that's what I'm going to be using to kind of demonstrate some of this. But in this, TI-36X Pro, you can do similar things in the Casio. But if you go to the table, you can actually put in a function. So I've already put this in, 12/5 x minus 9. It's good to know your order of operations. I did not need parentheses here because it sees the 12 over 5 first. And if I hit enter a couple times, I can start at minus, I don't want to answer, I want minus 5. If I start at minus 5, right, I can get, minus 5 and minus 21. I can get 0 and minus 9. Also, what you see here is if we come back to the negative 3 here, it does not, we get negative 16.2. So that point does not land on this line. Okay, so we could even keep coming here till 5 and make sure that we got the equation of our line correct, and 10 and 15. So big picture, there's multiple ways of solving this problem. But I wanted to show you a couple things. One with the calculator, one with kind of those point slope formulas, the y equals mx plus b formula, formulas of a line. Those equations are pretty important when you're just starting to look into basic algebra, basic geometry, and that sort of thing. So any questions, or if not, I think I'm just going to keep moving here and move on. Because as we keep moving here, we also go to equations of a circle. Okay, so equations of a circle, you might not remember the equation of a circle as well, and that's okay. I do have the NCEES reference handbook here. I'm just going to click on math and hope that it's there. Honestly, I've done this before, so I know it is there, but you can even see here, here's our equations for the straight line, the y equals mx plus b, the point slope formula. We see some quadratics, and eventually I think we're going to get to a circle somewhere down here. We see polar coordinates. Again, some of these things, there's so much here. Where do you focus your time? You do want to know the basics of polar coordinates. You do want to know the basics of trig for sure. These are some of those things where you got to know them. And as we come down here, we have different types of geometry, and eventually I believe we get to a circle. And on the test, you're not going to be wanting to just scroll through this. I'm doing this a little bit now just because it makes it easier to kind of to get a handle on it. But if I type in circle, right, I mean, this is where we have 18 matches, and on the test you're going to want to know what to type in, so the more familiar you get with this, or with the manual, the better. So I'm starting with conic sections if I'm going backwards here, and here we have a circle where we have a formula of a circle. So we also have a radius, which is x minus h and y minus k. So this gives us basically everything that we need to solve this problem. So I'm going to come back and use those formulas here to solve this problem. So I'm going to know that my equation of a circle, right? My equation of a circle is x minus h in parentheses squared plus, y minus k, again in parentheses squared, and this is going to equal r squared, sure, the radius squared. Okay, so the good news is we have h and k. We have h and k here. I'll turn my calculator off so you can see the whole problem here a little bit better. And we have a point that's going to be somewhere on the circle. So in other words, if we have a coordinate plane here, we're going to come over to 2, 4, and that's going to be the center of our circle. Then we're going to have our circle, and if we come over to like 5, 8, that point's going to be on it. Okay, so that tells us our radius here is going to be the difference between kind of this x and this y and the center, which is hk. Okay, so if we want to start there, we can do that. We can say, well, the radius equals, well, what's this going to be? It's going to be the square root of, because we're doing Pythagorean's theorem here. Basically, I'm going to, the x and the y are bigger than the h and the k, so I'm just going to put those first. But we're going to say x minus h, squared plus what? Y minus k squared. So this is just Pythagorean's theorem. Hopefully that's, again, one of those basic things that you don't have to go look up. You've done enough times that it should be second nature for you. So here we go. So as we go here, what do we have? We have this is x. So the square root of 5, what's this? X is 5 minus h, which is 2, that's going to be squared, plus y, which is 8, minus k, which is 4, that's going to be squared. And hopefully you've seen this before, but this is going to be our 3 squared plus 4 squared, and r is going to equal 5, right? So this is our 3, 4, 5 triangle, our beloved 3, 4, 5, which I love to use in like statics and that sort of thing when I'm teaching that class. So just one of those things that you should keep an eye out for. Okay, because oftentimes I think the FE is not really trying to make you screw up on like basics like this. It's they're trying to test you understand the fundamentals. I mean, honestly, you might just be tempted to say, okay, well, this looks like a circle formula. I'm just going to pick it and move on because I got 3 minutes for a question and I don't want to waste the time on it. But let's take a step back and look at it. So what we get here is x minus h, so x minus 2 squared, plus, what do we got? We got y minus k, which is 4. That's squared equals 5 squared. So this formula is really close, except that our x and our y are switched. So it's wrong. Okay, this formula is really close, except we don't have negative signs, so that's wrong. So we get into this other form here, and we're gonna end up being one of those two. But when you get, sometimes you see a problem and it doesn't look exactly the way you expect, and that's one of the things you have to watch out for on the FE as well. If it's not exactly like you expect, you can still make it work. Okay, so what we're going to do here is we're just going to expand these. So x minus 2, if that's squared, we're going to get x squared minus 4x plus 4. And if we have y minus 4 squared, we're going to end up with plus y squared minus 8x, or 8y plus 16 equals 25. Okay, and hopefully you're starting to see this, but if we subtract the 4 and subtract the 16 from both sides, that's subtracting 20. And what happens? So the 4's and the 16's go away. We end up with x squared minus 4x plus y squared minus 8y equals 5. Okay, and really quickly, hopefully you start to see this as well, but x times x minus 4 plus y times y minus 8 equals 5, and you see the answer. Okay, the answer is going to be right down here, which matches what we just came up with. So again, this question I threw in there for a couple things. I threw this one in there because it gets into Pythagorean's theorem, it gets into circle formulas, it gets into just looking at what happens when your answer doesn't look exactly like you want it to, right? Sometimes you have to do a little bit of manipulation there with the algebra in order to get it to work. Okay, so that's where we're going to go with this one. It's just a little bit different, but it sometimes it's easy as they'll give you this exact formula here. Sometimes you'll have to do a little bit of manipulation. So no questions there. I'll just keep moving on. All right, so this question, again, I threw this one in there for a couple reasons. One, because it shows you some basic, how to use, or basic algebra, really. I shouldn't say basic algebra. A series of three equations aren't like basic algebra. A series of 2 equations, that's a little bit more basic level. 3 gets a little bit more complicated. But Josh Wilson, I noticed you're on the line, man. I still credit you with showing me how to use my calculator, so I so appreciate this. But let's start there, I guess, because if you have a TI-36X Pro, this is a beautiful thing, because if we pull up the calculator, you could do a second system solve. And this is great because we can just do a 3x3 linear system. Okay, this is pretty amazing. I put these in already, so the coefficients 4, 1, and -2, right? That matches what's on the left here with equation 1, equation 2, right? The first coefficient, x coefficient 2, 1, 1, and then our constant term on the right is 8. On the left, or on the equation 3, 1, 2, 2, and 4. And the beautiful thing about this is once you go through, you can solve. So if you know how to use your calculator, we can see the 4, -6, and 6, equations. So again, you can save a lot of time if you actually know how to use your calculator. And if you don't know how to use your calculator, what's another alternative? Well, another alternative is to look for some things that are going to make your life easier. Like if you're doing this calculator is acceptable, yes. So what you want to do is you want to look for ways where you can do elimination or substitution. In this case, the first thing that jumps out to me is the coefficients on these two terms are multiples of each other, right? So what I can do here is I can multiply this whole top equation by 2, and when I do that, let's work this out by hand just real quick. So I get 4x plus 2y plus 2z equals 16. Okay, sorry, my z's looks a little bit funny there. And now when I take these next two equations, this series here, I can subtract one from the other. So x, minus 4x, I get minus 3x. 2y minus 2y, these cancel out. 2z minus 2z, these cancel out. So I get equal to 4 minus 16, or minus 12. Divide both sides by -3, and -12 divided by -3 is 4. And the nice thing here, again, we get that answer. You might have 2 answers with like a 4 in here or something, but this is the only answer that works. It's the only x value that works. And the interesting thing one of the things that I did here is you can't just pick this one and say, well, does it work for one equation? Because all of these work for one of the equations. Okay, so sometimes the answers are obvious, sometimes they're not. But in this case, you can use elimination, you can use substitution to solve for a series of equations. But yeah, this calculator, the TI-36X Pro, another reason I like to do the math session first is just to show you the power of knowing how to use your calculator on the FE, because for a lot of these math questions, you can plug them in and actually solve them using your calculator without like having to do a lot of crazy math. So if you get either, I'd recommend the TI-36X Pro or the Casio. Is it the FX115? I don't know. One of you guys online probably has that right now. But either one of those should work. And if you really like HP, you can go with HP. But you know, it is what it is. So definitely I'd suggest grabbing a good calculator and knowing how to use it. All right, we're going to keep going, and as we keep going here, we're at inverses. I mean, inverses, exponential functions, again, topics that I think could show up. They're kind of some of those basic manipulation topics, right? In inverse, you just flip the x and the y, and then you have to manipulate the equation. So this question gets thrown in there, not so much do you know how to use a log or what the definition of a log is, but kind of the idea of, do you know how to manipulate an equation? Again, one that's maybe a little bit more complicated than the y equals mx plus b or a circle formula, but do you know how to manipulate it, right? So with this one, where we're going to come down to is to get the inverse, we're just going to switch the x and the y. So x equals 3y. And it would be so nice if that showed up, you know, over here, but it doesn't. So what do we need to do? So we need to go ahead and actually take a look at this. So let's just come back to our reference handbook for a second. And if we come to logs, there are some identities in here for logs, in really, you know, the b to the c equals x. If b to the c equals x, so the log of x with base b equals c. And if you haven't done logs in a while, it can be confusing. Honestly, I hadn't used logs in a long time, and I had to help one of my kids with logs in their algebra class, and it took me a minute to go back. So I was like, hey, let's go there for now. So let's go to this side. And one of the ways that I'll look at this is, again, like with algebra, you can kind of do anything to either side of the equation as long as you do the same thing. And that's kind of an overstatement a little bit, but let's keep going here. Let's take logs of both sides. So if we take a log of x, and we take a log of 3 to the y, right? What happens? Well, this is one of those identities. Sorry about that. This is one of those identities, right? So what we have here is, if we come down to the bottom, right, what we see is one of those identities, log x to the c equals c log x. You see that? So we're going to come back and we're going to say, well, log 3 to the y equals y log 3. Okay, we can divide both sides by log 3, and I'm going to rearrange this a little bit, but what we get, you know, divide both sides by log 3, we get y log x over log 3. And this is your definition right here of y equals log x with the base 3. Okay, so this is, again, if you know how to manipulate some functions, this is going to help you on the FE, and if you can do that quickly, that's going to help you as well. But let's just go back and see that definition over here. As we come back one page, we see that log of x, you know, base a, log of b base a equals log of x base b. Okay. So, you know, whether it's knowing how to switch bases, or it's, you know, knowing that log of x y equals log x plus y, right? So, or log of x over y is like log x minus log y. If you have to deal with logs or natural logs, then knowing some of those properties are going to be helpful. All right. So again, kind of representative of exponential functions, logs, natural logs, and those different pieces. Are you going to get this exact problem? Probably not. But do you know what, you know, the natural log is versus the log, right? The natural log just has a base of e, whereas log of x typically has a base of 10. Okay, until we change it to a base of 3. Okay, but this gives us an answer here. It gives us, which one was it? It was answer C. All right. So we can keep going. Any questions? We good? I'm moving. It's late, you know, but we can do this, and hopefully it helps. And as we get into a rhythm here, hopefully you can do the same when you're taking the test and just get into a rhythm. Analytic geometry. Again, geometry gets into the algebra, it gets into the trig, it gets into some of these pieces where, oh man, you get into identities, and maybe you haven't used advanced trig in a while, and you forgot what a secant is, or you forgot what a cosecant is. I would recommend going back and taking a look at, especially the identity sheets on in the reference manual. So as you come down here, there's some trig identities, and you want to kind of get a basic understanding of what these are. So the cosecant's 1 over sine, the secant is 1 over cosine, right? And then there's some identities in here like sine squared equals 1, plus cosine squared equals 1, or tan squared plus 1 equals secant squared. So some of these identities, you're not going to memorize all of them, but hopefully you should. What is analytic geometry? That's a good question. It's kind of covers like everything. In a sense, it's like your algebra and into trig as well. It deals with plane systems, and it deals with like how you describe those plane systems. So it can get into lines, circles, trig. That's kind of the way that I think of it. So I throw trig in there for identities. We'll talk about trig when we get into calculus as well. But this is where you're given a question, and this kind of gets to some of the identities, right? I mean, you could try just plugging in numbers in your calculator and looking to see, like, does one of them work? Okay. Another thing that you can do when you get to identities like this is you could jump in and you could try to change some of these pieces so that you get everything in sines and cosines. That's one approach. But one approach might be here to come back and say, okay, well, how can I do that? And really what we see here is tangent is defined as sine over cosine. Okay, so if we come back and we say, let's just start plugging in and see what we get. So cosine x plus sine x times, we're going to substitute in, we know that tangent equals, and it's so easy to forget and screw these up, but what is it, sine over cosine? Okay, so sine x over cosine x, and if you screw it up, the signs will cross out and it won't work that well. But where do we go from here, right? What you see is you get cosine x plus sine squared x over cosine x, and you might be thinking like, man, I'm farther behind than I was when I started, but don't give up, don't lose hope, because as we come back to our identities, and the nice thing is when you're on the FE, you have 2 screens, so you don't have to keep flipping back and forth like I'm doing here. But this major identity is one of those real common ones. Sine squared plus cosine squared equals 1. You might be saying, why do I care? Because if I know sine squared x plus cosine squared x equals 1, I know that cosine, I know that, let me write it this way, I know that sine squared x equals 1 minus the cosine squared of x. So now I can take this value here and I can substitute it in over here. Okay, so I can say, well, the cosine of x plus 1 minus the cosine of x squared of x all over the cosine of x, and things are looking a little bit better here. So I get cosine x. I'm going to separate this fraction here, 1 over cosine x minus cosine squared of x over cosine x. You'll see that the cosine squared and the cosine, they cancel out, so we're left with cosine x plus 1 over cosine x minus cosine x is the equivalent, the equivalent function here, or expression, and we're left with 1 over cosine, which, if you remember, and some of you probably need to go back and look at the reference handbook again, but 1 over cosine is equal to the secant, right? So that becomes our answer. Make some sense? But again, are you going to get this exact question? No, but could you get a trig expression where you have to find equivalency and do some substitutions and some manipulation? I think that's pretty likely. Okay, so being familiar with those identities, going back and looking at them again, because maybe you haven't looked at them since calculus, it's probably a good thing to do. All right, so Matt, I don't know, maybe this is more a calculus question, but even still, it describes the physical universe in a plane system. Okay, let's go back here, and the reason I threw this one in is, again, one of the things that you need to know how to do is you need to know how to use your calculator. And this is so easy to mix up and so easy to mess up that I thought I'd throw it in, because again, when you're looking at how to use your calculator, you want to be able to solve it quickly and solve it correctly. Okay, we can do this one of two ways. We can say, well, we can say that x equals, x equals pi over 2 radians is equivalent to what? Well, this is equivalent to 90 degrees. Do you know how to do that? I mean, basically we're taking this is times 180 degrees over pi, right? So we can get to degrees or we can use radians, but you need to pick which one to use and use it. You need to pick it and use it because it's so easy. Like, for example, to go into your calculator and say, okay, well, I can take the cosine of 90 and get a certain value. And is that the right value? Well, it depends. This is where you need to look at your mode. What you'll see here is right now I'm in radians. Okay, that's the problem if I'm using degrees for my angle. So I can come back here and use degrees. Okay, one of the things that I want to point out though is when you switch back from mode radians to mode degrees, all my history, actually my history isn't gone. Look at it, it's still there. So that's good. So I can come back and do cosine 90 again and get a different answer. Okay, because now I'm back in degrees. So I know that the cosine of 90 degrees equals 0. Okay, so the question is, it's not equivalent to which of the following. So each of these are going to equal 0 except for 1. So now I just need to go through and evaluate. So the tangent of 2 times 90 degrees, this is going to be the tangent of 180 degrees, right? So the tangent of 180 is going to be 0. Okay, so that one checks, and it's not that one. Okay, we can come back, we can say, well, what about the secant of 2 times 90 degrees? So what's that? Well, it's like the secant of 180 degrees, which is also like 1 over, do you remember which one it was? The cosine or the sine? Let's just come back and double check, right? What is that? Secant is 1 over cosine, right? So this is going to be 1 over cosine of 180 degrees, which, if you don't remember, cosine of 180 is did I do that right? Cosine 180 is -1. So 1 over -1. And what you'll see here is I made a mistake because it's so easy to lose some of these pieces. The +1 I lost, so it's easy for me to take this and move it over a little bit and add my 1 back in. But just be careful because it's so easy, especially when you're trying to go fast on a test, to make some of these mistakes where you miss part of the problem and you make a mistake. But -1 + 1, this is going to also equal 0. Okay. So we had A, we have B, we have C. 2 times the sine of, what do we have? 2 times the sine of 90 degrees. And I'm going to put this square out here because that's kind of how we end up doing it in the calculator. Okay. -1 equals what? Well, if I come back and I type the sine of 90, I get 1. So 2 times 1 squared minus 1, and all of a sudden we see something. Well, 2 times 1 is 2, minus 1 gives us to 1. So this is a strong contender because it doesn't equal 0. But just to make sure we didn't screw something up, let's go to D. And the cosecant of, what do we have, of 90 degrees minus 1 is equivalent to 1 over the sine of 90 degrees minus 1. So if, again, I have the sine of 90, I already have that here. The sine of 90 is equal to 1, so 1 over 1 minus 1 equals 0. And we can cross out D as well and be certain that our answer is this one. Okay, so again, knowing some of these how to use your calculator is going to be important. Knowing that mode, whether it's degrees or radians, pick one, but just be consistent. I'd say be consistent with what you do, because if you're flipping back and forth between radians and degrees and you're trying to go fast on the test and you see a problem like this and you say, okay, that's radians, I'm going to switch it to radians, and then you get to another problem later on and it's in degrees, that could make it a little bit more challenging because you could get it wrong. Okay, so hopefully that works. If you have questions, shoot them out there. Okay. Let's keep going here. We're still in kind of this geometry section, and I bring up right triangles and similarity here because I use these a ton when I teach trusses. So when I teach trusses, the idea of similar triangles is huge. So when you have a perpendicular line like, like this, like AM that shows up here, now all of a sudden we have a bunch of similar triangles. Okay, so I can label some angles here, but if I label this angle alpha and this angle like beta, okay, what we see is we have a whole bunch of similar triangles. So we have the big triangle, right? We have the big triangle here. That's our big triangle. And then we have two smaller similar triangles. So we have one similar triangle that looks like that, and another similar triangle that looks like this. And when we start looking at these similar triangles, we can relate them and come up with some relationships here. So what I'm going to do is I'm just going to take a look. I'm going to take this first triangle out. I'm going to take, this B or AMB out, and I'm going to look at it. I'm going to write some relationships here. So what I really want to find from this triangle is I want to find a couple things. Like, we're going to get rid of calc. Oh man. Would love to. Thanks, Josh. So what we're gonna do here is we're gonna go, and what we're gonna do is we're gonna say, let's take a look at this. So AM, right? Well, let's say we want to find this line AM. AM over, what do we know? We know AM over 5, right? Because we have this line over the hypotenuse is going to equal what? It's going to equal the long side of the big triangle over the hypotenuse. So this is going to equal, essentially, what do we have? We have AC, wrote it in the wrong spot, divided by BC. And you might say, well, we never solved BC, but this is where, again, if you know some of those basic triangles, and if you don't, you can use Pythagorean's theorem, but this is a 5, 12, 13 triangle. So the hypotenuse is 13. So we're going to get AM over 5 equals what? AC, which is AC is the equivalent of 12 over the hypotenuse of 13. So I'm just going to write that AM equals, well, if we multiply both sides by 5, we get 60 over 13. Similar triangles, if you can see the similar triangles, it's going to help you a ton when you get into things like trusses. Even in some of this stuff, it's going to help. Okay, let's go to the next one. Let's go to BM. So BM we're trying to solve for, so I'm going to say BM over the known BA or AB is going to be 5, is similar to what? The short side of 5 divided by the hypotenuse of 13. Okay, so similar triangles again here. So we get BM equals, well, now we have 5 times 5, so 25 over 13. And here, let's go to our last triangle. I think we're seeing an answer emerge here, but if we go to our last triangle, what we can see is now we want to solve for, I think this last one, CM. So we're going to solve for CM over, what do we know? Well, we know CM, and we know this value here of 12. So CM over 12, okay, equals what? It equals the long side over the hypotenuse, right? So the long side is 12 over 13, and we get CM equals 12 times 12 is 144 over 13. And what you see real quick is the 13s are all common, they go away, and our solution is going to be the 60, 25, 144 ratio. Okay, so here we have similar triangles, and something that's gonna come up at some point in some way is similarity, I believe. So something to be familiar with, how to relate those, whether it's on a problem like this or it's a truss. You're gonna want to know how to relate one side of a triangle to another. All right, so let's keep moving here. This one I threw in. I had the idea of doing this one, and then I actually went to try to do it in the reference handbook and was surprised. Because this is just like, okay, in the reference handbook, as you're scrolling through the reference handbook, let's go back to the reference handbook for a second. And what you see is in the math section, there are areas and volumes, and we have parabolas, we have, we have ellipses, we have circular segments, and I thought to myself, great, this looks good, we'll do a circular segment, use something that's one of the more complicated ones. And all of a sudden I realized, wait a minute, this has R, it has phi, it has S over R, but we don't have a lot of this stuff. So in this problem, what we're asking for is an area, right? So we have a couple areas. I mean, we can have an area of like a trapezoid here. We could find that area. We also have an area here of like this circular segment, okay? I had a student actually, I think, Matt, I don't know if you're online, but you were doing this and you just sort of said, I'm going to do it a little bit differently. I'm going to call this a parabolic section, and I think he got pretty close, okay? But what I want to do is I want to go ahead and solve this as the two areas that I drew originally. So I want to show this as a trapezoid and a circular sector. I mean, it's just, again, there's going to be areas. Are they going to be exactly these two? I don't know, but can you go to the reference handbook, find the right area formula, and use it, right? So here we have some area formulas, and these are dependent on the radius and D and phi, and what you realize is all we have is this radius, and that's about it. I mean, we know this length here, this chord length, but we don't know a ton else. And that's where sometimes the reference handbook is a little frustrating, because you look at this and you think, like, that doesn't give me enough. But maybe something clicks in your head and says, wait a minute. In transportation, we did a lot with horizontal curves. We did a lot with other things along those lines. If I come down to transportation here, and transportation's when? It's after structures, right? So if I come to transportation, if I get there eventually, actually it's after environmental. Sorry, I should have gotten there more quickly. I probably should have done a search for this. There's transportation, right? So we get into transportation, and in transportation, we have some more equations. So here's vertical curves, and here's horizontal curves as well, which is interesting because we see in here, we see a formula, R equals the length of the chord divided by 2 sine I here. That was phi in the other one. So let's solve for that first and then kind of go back and work the other equation. Okay, so when we come here, let me just label a couple things. We're going to find area 1, we're going to find area 2, okay, and we're going to use a couple of these different formulas to do it. So area 1, hopefully, I'm just going to get that one out of the way because area 1 is just a trapezoid. So what's this? This is height 1, so 12, plus height 2, which is 6, all over 2, so that's the average height times the width of 8, and that's going to give us one value. So 12 plus 6 divided by 2 gives us 9 times 8, and that's 72 square meters. So we know we're in the right ballpark. Now we're just seeing, well, how much does that little segment, this little sector add? And this is, maybe this isn't a 3-minute problem, but maybe it is. I don't know. What we got from the transportation section was R equals what? It equaled LC, so the length of the chord, divided by 2 sine I over 2. Okay, so we get this, and what do we see? Well, we know that we can find the length of this chord. We know the radius, so we get essentially 11 meters equals the length of the chord. And hopefully you see this, but again, I like these 3, 4, 5 triangles. We have an 8, 6, 10 triangle, so the length of that chord is going to be 10 meters divided by 2 sine I over 2. So we can manipulate this again, and when we do that, I believe what we get here is, well, let me make it a little bit simpler here. We get 2 sine I over 2 equals 10 over 11, or we could say sine of I over 2 equals 5 over 11, where we're dividing both sides by 2. We can take the inverse sine of 5 over 11, sine inverse of 5 over 11. This is going to equal I over 2. So from that, I believe what we get is I equals 54.07 degrees. Anybody else get there? So this gets us this sector angle. So if we're looking at a bigger picture here, this is some radius, right? And this angle here is going to be 54 degrees. Okay. And now once we have that value, we can come back and go to our area section here. So if we come back to our math section and come down to our areas, right? We have a area formula here that's r squared phi minus sine phi over 2. So let's come back here and we get the formula here for that sector, for that segment of the circle, and we get A2 equals r squared times phi minus sine of phi over 2. And some of you, if you have a calculator, you might be thinking like, uh-oh, how do I do this? Thanks, Matt. So just like your comment, you got it. 6, 8, 10, 6 squared plus 8 squared plus 10 squared or equals 10 squared. That's our Pythagorean theorem there. So perfect. I love you guys. You guys help out so awesome. So if we plug some of this stuff in, you're gonna want to know not only what the equation is, but how to use it. And this is where it gets a little dicey because we know the radius is 11. So I'm just gonna drop the units here for a second. Oh man, and now what we have to worry about here is honestly, we have to worry about radians and degrees. This formula is in radians. Okay, so we need to put things in essentially in radians here. So I'm going to take my 54.07, I'm going to multiply it times pi over 180, and I'm going to get I equal to, what is that, 54.07 times, well actually I'm just going to divide it by 180, and I'm going to leave the pi in there. I'm going to get 0.3, so this is basically 0.3 pi. Okay. Did I do that right? No, I think I did something wrong. What did I do wrong? Anybody got it? Oh, because this is this I over 2 or is this I? So I think I don't know. Let me back up and make sure I got this right here. Let me back up and make sure I got this right. So let me pull the calculator up and we'll take a look here. So if I bring the calculator up, let's do the inverse sine. And to do the inverse sine here, I'm going to hit sine twice. 5 over 11. I get 27. So yeah, so if we multiply that by this 2, we get 54.07. Okay, so that works. So let's see what we get. So if we're looking at radians here, my notes are a little sketchy here. This is bad, but let's see what happens. We get, I think I just dropped a pi, but I think we have the 0.3 pi up here. Okay, 0.3 pi minus the sine of this 54.07 or 0.3 pi. Okay, all over 2. Sorry, let me get rid of the calculator there. So this is a little bit interesting on the calculator when we get to it. But if we put it in here, right, we get 11 squared, right, times 0.3 pi minus sine of 0.3 pi. And you might be thinking, am I in radians or degrees? I don't know. That's a good question. Let's check. I'm going to divide that by 2. I'm going to come back here, go to my mode. I'm going to go to radians. And if I hit enter, I get like 8.07. And that is the correct value. So 8.07 square meters. When you add this 72 plus the 8.07, you actually get this 80. So yeah, the parabola equation is so close to this, and it's so much easier. So that is a huge, exactly, the parabola equation, you have the 2bh over 3. 2bh over 3, right? That gets you essentially to 80 as well. So what's our base? So 2 times the base, 8 times the height, 6 over 3. That's going to get us what? 2 times 8 times 6 over 3. It's going to get us 32 square meters. So if we're looking at, let me just do a different color here, but if we're looking at, this area here, that's, this is an approximation. It's not exact, but it's really pretty close, and it saved us having to go to transportation. It's not exact because this is a circle. The radius of 11 is a circular segment. Okay, it's not a parabolic segment. It's really close to a parabolic segment, but it's not a parabolic segment. So, if we look at this differently, have these other two sections here, like we could say essentially like 8 times 6 equals what? That's 48 for this blue section, right? We could do this a couple different approaches, and honestly on the test, your approximation is going to be okay. It's going to be close enough, but this is where that circular segment, sometimes you have to pull formulas from different sections of the book. Okay, so I don't know, good questions, but the precise answer is to get the circular segment, right? This formula here is for the circle, or the circular segment or portion. Okay, and that's the precise way to do it, but again, you have to know whether you're using radians or degrees, and it gets a little bit tricky. So know how to do it, and you guys should be good. But also use the formulas a couple times, because you can look at the formulas, and until you actually start plugging numbers in, you don't realize that formula is in what's up, Justine? That formula is in radians. Okay, so definitely check that out. All right, this question I actually took from my son who's in algebra, and there's a way to solve this algebraically, but I thought it was interesting because when I saw it and he was working on algebra, I thought, like, man, why would they have this type of a question in algebra? This is a calculus question. Okay, and normally this type of calculus question, you're doing something different. Normally when you have a parabola, you're looking to find like the minimum point, okay, or a maximum. And if you remember how to do that, what you're going to do is you're going to set the derivative equal to 0 and figure that one out. So in this one though, it's you're not finding minimum or maximum, you're actually just changing the slope. So we want to find when that slope equals to what? To 2. We want to find when that slope equals to 2 and essentially figure out this b value, which is going to be and minus b is going to be our y-intercept. So that's what we're trying to do. So when we get started here, we're just going to take a derivative f prime of 1 x is just going to equal 2x minus 4. So we know the slope. Again, we know the slope is going to be 2 at that point, because this question's saying we want these line segments to be parallel or tangent at a specific point, and tangent means the slopes need to be the same. So we know the slope of the line is going to be 2. When does that happen? It happens when the first derivative equals 2. So 2 equals 2x minus 4. So what does that mean? It means if we add 4 to both sides, we get 6 equals 2x, and x equals 3. Okay, once we know x, we can plug that back in. Not f prime, but f of x, f of 3 equals what? We have 3 squared minus 4 times 3 plus 2, and f of 3 equals 3 squared is 9, minus 12 is minus 3 plus 2 is going to be, I think, minus 1. So all of a sudden we know where this point is. We know this point is, what is it, 3 comma minus 1, and now what we need to do is we just need to solve kind of this formula for b. So we know f2x, in other words, we have minus 1 is our value when x equals 3, so 2 times 3 plus b, and if we do this out, we get minus 1, so this is f2, minus 1 equals 6 plus b. If we subtract 6 from both sides, we get b equals negative 7. So this is f2 at, just for clarity here, at 3 comma minus 1. And we just solved, for b. which means we have an answer here and we were able to do it. Okay, so you probably won't, maybe you'll see this question, maybe you won't, but the question of maximum minimum, you know, when does the slope equal to, or when does the slope of your parabola equal zero, you've done all along in calculus. This one takes it and twists it a little bit, right? And a lot of times that's what the FE is going to do. It's going to take a basic concept that you know and twist it just a little bit to see, do you understand the principle or just how to apply straight things? Okay, and this is same principle as finding a max or min. It's just instead of finding a max or min when the slope equals 0 on the parabola, you're just specifying when the slope is or what the slope is. Okay, so kind of a cool question in that sense. Oh, more calculus. I wish we could do derivatives on our TI-36X Pro. You can do some. You know, I don't know. Actually, somebody tell me. Can you actually do derivatives like this? But yeah, seeing this is being recorded, you can come back. Even if you can't, let's go over how to do derivatives. And there's different derivatives. I'm just going to come back here for a second to the reference handbook, and if we come down to derivatives, we have some different formulas, and I just picked one of them. Okay, so this question is going to deal with the derivative of u v dx, and we get a formula u dv dx v du dx. So we'll go through this one, but you want to be familiar with these various formulas, you know, whether you're integrating, you know, sums or constants or products of two functions, or potentially, you know, an exponential function. So we're just going to come back here, and I'll write this down, right? But the formula that we came up with, or that's in the reference handbook here, is du v dx equals what? It was u dv dx plus v du dx. Okay, so this gets us a formula. So we need to define these. We need to define the derivatives, and that's where we need to go next. So u equals the cosine of 2x, v equals e to the 4x, and now we want to take derivatives. So du dx equals, oh man, do you remember the derivative of cosine? If not, you're in luck because it shows up here, right? The derivative of a cosine is the negative sign. So if you don't remember it, it does show up. You just have to know where to find it in the reference handbook, okay? And if you're not sure, you can find it. But this is 2x, so what happens there? So let's come back here. Derivative of cosine u is minus sine u du dx. So we have to also take the derivative of what's inside the cosine. So this is going to be minus sine 2x times the derivative of this 2x, which is going to be times 2, and I'm just going to throw that back over on this side. So minus 2 times 2 sine x, dv dx. If you can't remember derivatives of exponential functions, what do we have? Does that show up here? E to the u is e to the u du dx. So it's very, very similar, and we get this. We take the derivative of the inside part. We get 4 e to the 4x. And now we just gotta plug and chug a little bit here. We'll take these different parts. We'll say cosine 2x dv dx, which is times 4 e to the 4x, and then we're gonna add v, which is e to the 4x. Times dv dx, which is going to be minus 2 sine of 2x. And hopefully what you see is some common pieces here. So this e to the 4x is common. We can factor that out, e to the 4x. What's left? We get 4 times cosine 2x plus, what do we have left? Well, actually I'm going to take that away because we have a minus sign here on the 2. So minus 2 sine 2x. And fortunately that matches something in here. I did my homework this time. So fortunately that matches something up here, and we get another answer. Okay, not too crazy, but you have to know how to do those derivatives. You got to know some of these functions, and you get the answers. So vlog, did you factor out an extra 2? You did, which is fine. That's actually a little bit more simplified, but yeah, I mean, we could have factored out the 2 from this 4 and from this 2. That would have been a little bit better, but I think you lost the 2 on the cosine 2x. So take a look at that. All right. Okay, so or you lost the 2 somewhere. I don't know. Yeah, take a look. Okay. So let's keep going. If functions below intersect at two locations, create an enclosed area. How come A and B are the same? A and B, did I make them the same? Because I screwed up. Thanks for the question, Margaret. I probably should have made these different. But if you get a repeat answer, it probably means the question's bad and somebody didn't do enough QA, QC. So I did check these to make sure that the right answer was in there. I screwed up on the wrong answer, so I apologize for that. I will fix that. That'll be like version 1.03. Okay, so let's keep going. But thank you. Functions below intersect at two locations, create an enclosed area. Area bounded by these two functions is most nearly. So this gets to a definite integral, right? Basically what we have is we have two functions, and if we look at a coordinate plane here, one thing that to notice real quick is they both have this +1 term. So they both have the same y-intercept, right? We know that they're both going to intersect kind of at this +1. The x plus 1 is kind of an easy function, right? This is your f2. And what we see as well is we have this negative sign. So we know our parabola is negative. It's going to come back down. So it's going to go through here and back down. And there's our parabola. There's f1. What we're trying to find here is this area bounded by the two curves. So essentially all that we're doing here is we're going to take the integral, right? Integrals find areas of basically from 0 to x. Or I shouldn't really call that x. I should call it like 0 to a or something. But 0 to a, my integral looks like a weird row. Integral from 0 to a of f1 minus f2. And I'll put a dx out here, kind of for completeness. Okay, but we need to do two things. We need to find a, where do these intersect? And we need to then take the integral. Okay, so what we'll do is we'll start by first finding a. To find a, we're gonna say, well, f1 has to equal f2. Okay, so what does that look like? I'll just write it out. Minus x squared plus 4x plus 1 has to equal x plus 1. And right away some things can cancel out. The ones can cancel out. We get minus, I'll put that minus x squared over here. Actually, no, I'm just going to leave it this way. We get minus x squared. We can subtract an x. Plus 3x equals 0. We can factor this. We can take an x out. So we get x times 3 minus x equals 0. So we get x has to equal what? It has to equal 0, or x has to equal 3. So this solved a. Essentially, we know that this integral is going to go from 0 to 3, right? This is kind of our a value over here, where this point of intersection is. Okay, that's our a value, our 3 value here, and I probably should have labeled a closer to that, not the x-intercept. Okay, so that means what we need to do here is we need to do this integral from 0 to 3 of our minus x squared plus 4x plus 1 minus x plus 1. That needs to be in parentheses. And honestly, we kind of already did this a little bit, because on this side we did this, and we know that this is the integral from 0 to 3 of minus x squared plus 3x. Okay, so you can do that integral out, but for the sake of showing you something on a calculator, I trust you guys have all taken a calculus class. I do want to show you this. This is kind of cool. You can go to the second integral function in your calculator and actually do definite integrals. So you can do it in this mode. I kind of like, when I'm doing definite integrals, to go to math print. If you go to mode and go all the way down to the bottom and go to math print, and then to do the integral, it just shows up so much nicer. And I wrote this wrong. This is 0 to 3. But let's enter the sentence. 0 all the way up to 3 of what? Minus x squared plus 3x. Okay, and hit enter. You wait. It's moving. You see the thing, and we get 4.5. I mean, honestly, it's that easy. Sort of, right? If you know how to use your calculator, it can be that easy, which is nice. I mean, we could do this integral. We could say, well, it's minus x cubed over 3 plus, 3x squared over 2 from 0 to 3. The 0 goes away, so this just works out to be what? Minus 3 cubed over 3 plus 3 times 3 squared over 2. And I think you should also get 4.5 here if you do it that way as well. But I thought this would be a cool way to show you how to do a definite integral on a calculator. And again, it's figuring out how to use your calculator to work for you on the exam, because there's a lot more room for error, I would say, on the exam in something like this than there is just on the calculator and putting it in on the calculator when you're doing a definite integral. I don't know, use it. Single variable calculus. Again, we're doing calculus. You might have an indefinite integral where you don't have certain limits where you're going from 0 to 3, but you have to evaluate that integral as well. So let's take a look at this. Again, this kind of becomes a trig identity. You have to, come back here. And there are some indefinite integrals here, right? But as we come down, the reason I picked this one is because you don't see the integral of secant squared. You see the integral of tangent squared, that's great. But I don't see the integral of secant squared here in this form. And that's where, again, if you know a little bit of some of the other identities, it's going to help you. Well, let's come back to the derivatives for a second. Because one of the things that we see in the derivatives is the derivative of the tangent is the secant squared. So the integral of the secant squared is going to be the tangent, right? So if we're looking at this, we can use some of the information, maybe not directly, but indirectly, to solve our problem here, right? So this is going to be useful. Another identity that we could use here, where did it go? Where are our identities? Another identity we could use here is tangent squared plus 1 equals the secant squared. Okay, so a couple identities here that are going to help us. So I'm going to build off of this one and come back to our problem here. So we know that we know that the identity that we just looked up was the tangent squared of theta equals, or x in this case. I'm sorry, the tangent squared, what was it? It was the tangent squared plus 1 equals the secant squared. So, sorry, wrong button there. So the tangent squared plus 1 equals the secant squared of x. Okay, so we can rearrange this a little bit, but we can get, well, the secant squared x minus 1 equals the tangent squared of x, right? And all of a sudden, we can take this and we can substitute in, and we get the integral of the tangent squared of x, which actually does show up on our identities table. Okay, so a little bit of manipulation, we get the integral of the tangent squared, and we get tan x minus x. So this equals tan x minus x, and we'll throw in the constant there for completeness. Okay, so again, you might not be given the exact thing that's on the identity, but maybe with a little manipulation you can get there. So if you get familiar, do some practice with those identities, it should help. Okay, let's keep going. The next couple ones, I mean, I'm going to show you how to do them kind of both ways, but vector operations are going to show up on the FE in some way. I've talked to people that have taken it, and they do show up in some way, whether it's a dot product, it's a cross product, it's what that cross or dot product means. So we're just going to throw these in real quick. And actually, before we even do that, what I'm going to do is I'm just going to pull up my calculator and throw them in the calculator. So you'll notice on the calculator there's a vector, so I'm going to come to second vector. I already have these put in here, so I'm going to go to edit. You can see if I come to vector u, I got 5, 4. Actually, no, this is a different 5, 4, and minus 3. Okay, 5, 4, minus 3. And if I come back to second vector, I'm going to edit v, and it's 3, and it's going to be what? It's going to be 2, minus 3, and 4. So this is kind of like I, J, K, X, Y, Z, and these are our values here. So I can come back, I go to my vector, I can check them, just to make sure I got them in right. 5, 4, minus 3, and if I come down and get this, I get 2, minus 3, and 4. Okay, so once I have that, I mean, I can just come in to my vector, I can do my math and dot product. I can say come back to a vector again, second vector. I can pick vector u, and then I'll put a comma in here, and again pick a vector, and this is going to be vector v. And what does this do? It just gives me a dot product, gives me a scalar, and the answer, without doing really any hand calculations, we get is minus 14. It's a scalar. A dot product gives you a scalar. It gives you one value. I mean, what the dot product is, a dot b equals essentially ax times bx plus ay times by plus you know, az plus bz, right? So that's just going to be what, 5 times 2 plus, you know, 4 times minus 3 plus minus 3, or minus 3 times 4, and we should get minus 14 here as well. Okay, but in the calculator you can do all of this and hopefully do it quickly. Okay, so that's where you have to be careful with what you're doing. This is not we don't get a vector from a dot product, we get a scalar, okay, which is just the one number. And then what do we do down here for cross products? Similar thing. I'll pull up the calculator. It's the same vector. I tried to do that to make it a little bit easier here, but I can come to second vector again and go to math, cross product, right? So cross product of the second vector, there's a lot of seconds going on in here, but this is comma second vector and v. And what do we get? We get a vector now that's 7, minus 26, and minus 23. So again, what we see there is we see an answer that works. I'll show you how to do this quick, but A cross B. Normally what I like to do this is just draw it out, kind of that looks something along these lines. Resolution's dying on the stream here. We'll see how that goes. But basically I'm going to write this out: 5, 4, minus 3. You guys still have decent resolution on your side? 2, minus 3, and 4. Okay. So if we go there, what we're gonna get is basically we're looking for how to solve this, and basically the I term we're gonna look at. We're gonna look at these components, and we're gonna take the determinant for those components. So the determinant for those components is going to be 4 times 4 minus 3 times minus 3. And what's that? That's going to be 16 minus 9 is going to be 7. So the nice thing about doing some of these by hand is you can cross a couple of them out real quickly. We can come to like the j term. You see, you know, these two look the same, but let's go to the j term to see which one. So the j term, we're going to go kind of like this. We're going to go this way. So we're going to take the determinant that way, and essentially if we look at this, it's going to be like minus 3, 4 and 5, 2. We're going to take that determinant, and what's this going to be? It's going to be minus 3 times 2 minus 5 times 4, which is also going to give us minus 26. And we could do k as well, and that would just be the determinant of 5, 2, 4 minus 3 here, but that would get us out to the same answer as we got on the so as we got here. So so you're saying this is wrong? So hopefully the calculator's not wrong too. You know, I know I make mistakes at times, but hopefully I didn't screw something up. So if there is something wrong, let me know. But I think we entered it into the calculator right. I think this is going okay. But let me know. I don't know. Tell me what you guys think. But if it is, just drop some comments, and we'll go from there. Okay, so let's keep going. So let's keep going, and what we'll do here is we're going to do vector summation. We're almost done. I mean, like if we add these two vectors, I can do the same type of thing. I can add them in the calculator, but with adding them, it's pretty basic here. I can add, you know, a plus b, and I'm just going to add the term. So 5 plus 2 is 7i. You know, 4 minus 3 is plus j. Minus 3 plus 4 I lost the k there. Is that what you're saying? Oh man, you're so right. I lost the k on these vectors. So there's my k hat. So thank you. I will fix that. I totally lost that and nobody else saw it, including me. But yeah, so there's the k, there's the k, there's the k, and then we keep working, and it makes all the difference in the world. So thank you. So -3 plus 4 is going to be plus k. Okay. So as we go through this, what we're going to get here is B looks so right, but it's just so wrong, because what we've missed here was the unit vector. Oh man, so what's the unit vector? Well, if this is equal to some vector C, right, here's vector A, here's vector B, the unit vector is going to be what? The unit vector is going to be essentially C over the magnitude of C. So we have to go and find the magnitude of C. The magnitude of C is just going to equal the square root of 7 squared plus 1 squared plus 1 squared, which is going to, I think, work out to be, what, 7 squared plus 1 squared plus 1 squared. And if we take the square root of that, we're going to get the square root of, I think that's 51, is like 7.14. Okay. So this is in the reference manual, yes, but basically we get 7 over 7.14 I plus 1 over 7.14 J plus 1 over 7.14 K. And I believe the right answer is, somebody can check me on this, but I believe the right answer on this one is going to be the last one here, D, when we take 7 divided by 7.14. We get 0.98. So yes, this answer here looks so right, but you just have to be careful with what the question's asking. Okay. And lastly here, I think I got my IJs and Ks all right, so hopefully it didn't screw too many people up. But where are we going with this one? What we're going to do here is we're going to take a look at A and B, and we are going to say, well, this is kind of a little bit more of a conceptual problem, and this is where it helps to kind of have a little bit of an idea of what this means. So if A and B are perpendicular, what does that mean? That means what? The dot product is 0. So if A, so this is just something to know, and these are identities you'll find in the reference handbook. So if we come to vectors in the reference handbook, did I miss them? Matrices, vectors, right? This kind of, does this tell us here? I don't know that it does. For some reason I thought that we saw this in here, but maybe not. Okay, so here it is. If A dot B equals 0, then either A or B is 0 or A is perpendicular to B. If A cross B is 0, then A equals 0, B equals 0, A is parallel to B. Well, if we come here, these are two-dimensional vectors. They're not that crazy. We can actually plot these, right? So if I take a coordinate plane here and plot these, right, this isn't too crazy. I can come over 2, up 4, and this is like vector A. I could come -1 and up 3, and this is, you know, vector B. So now the question is, are they perpendicular? Well, no. Are they parallel? No. Are they, you know, this would mean A dot B equals 0. This would mean A cross B equals 0. So I'm just throwing these out there. A is the same length. This would mean the magnitude of A equals the magnitude of B, which, I mean, we could calculate that out to check. So let's check. The magnitude of A equals what? It equals the square root of 2 squared plus 4 squared. The magnitude of B equals what? The square root of 1 squared plus 3 squared. So what do we get? 2 squared plus 4 squared. Oh, let's put it on the calculator here. So we get what? The square root of 2 squared plus 4 squared. Squared. 2 squared of 5, or 4.47. And if we do the same thing here, square root of what? 1 plus 9, that's the square root of 10. And if I hit my my decimal converter here, I get 3.16. So we know that these aren't the same length. Okay, and we can prove that A is at an angle of 45 to B by using the definition of a dot product, really. So A, actually, let me come back here. What we're going to say is A dot B equals the magnitude of A times the magnitude of B times the cosine of theta. So if we look in the reference manual, we see that identity in here, I believe. Here's our dot product identity, right? A, magnitude of B, cosine theta equals, A dot B. So that's going to help us a little bit here, but we could dot these two. What do we get? We get, if we dot these two, 2 times minus 1 plus 4 times 3 has to equal essentially 4.47 times 3.16 cosine theta. So could you have stopped at earlier? Yes, you could have stopped earlier because the 3 other ones didn't work. But I just wanted to show you this kind of for completeness, because what do we get? We 2 times minus 1 is minus 2. So on this side we get 10 equals essentially 4.47 times 3.16 cosine theta. If we get cosine theta all by itself, I'm going to turn my calculator off here, but what we get is we get cosine theta equals, essentially, if you do this math out, it actually comes out to square root of 2 over 2. And that means theta is equal to 45 degrees. Okay. So kind of a long process here, but I wanted to show you, use this to kind of talk about some of these properties, but also show you how to apply the dot product in, with the magnitudes here. So something to consider, something to think about here. All right, we're getting down here. Sample of 6 concrete cylinders. Again, you can put these in. You can add these up all by yourself. I mean, you could come up and you can take. You could find the mean, which is going to be your x bar. You can find your standard deviation, which is going to be your sx, and mean is just the sum of x over the number of samples, and the standard deviation is going to be the sigma of x minus x bar all over n minus 1. So those formulas are in the reference handbook. You can go look them up. But this one just screams, don't waste your time. Go into the calculator, use how to use a table, actually use a data table here. So we can go into data, we can enter in some values. So I'm just going to enter these in: 3,900, 4150, 4450, 4350. I missed 4275 and 4250. So that's all 6 terms. And then if I go to second data, I can get 1 variable statistics. Data list 1, frequency 1 is fine, and I can hit enter a couple times, hit calculate, and we get x bar. So if you know that x bar is the mean, you're good. You get the 42,229, and then it's a question of what's sx. Is it 190 or 173? And here the standard deviation, if you know what that is in your calculator, you're going to know that the right answer is going to use sx, which is the sample standard deviation, which is typically what we're going to use. Okay, so another one of those ones where if you know how to use your calculator, it's gonna be helpful. All right. So let's keep going. Just a couple questions left, and then we'll call it a night here. But question 18: concrete mix produces normally distributed concrete with a mean strength of 4,400 psi, standard deviation of 200 psi. So typically, when you create concrete, you're going to have some uniformly distributed curve. You're going to have some mean value here, and you're going to have some standard deviation. And what you want with the concrete is you want it so that you set the target mean high enough above so that 99% of the time you're going to be in the green zone. There might be one breakout of 100 that gets low, okay, but not crazy low. It's going to get just a little bit low possibly, okay, but you want to set that target mean high. So the question is, what's the where is this, how does this work? And this again screams, this screams, it doesn't just scream, it tells us, I'm not going to put that in red, I'm going to put this in yellow, but that screams a normally distributed concrete. So what we can do is this brings us back into kind of the statistics section of the reference handbook. So if I just go in and type in normal distribution, right, this is going to help me to find what I'm looking for. And it's going to help me. I mean, I can come down here, I can look all sorts of things up, but really where this is going to go is it's going to bring me back down to eventually, if I keep coming here, it'll bring me to like a z-test, and this is gonna give me some statistics here. I'm gonna be able to find what I'm looking for, and I'm gonna be able to come down one more here and take a look. So essentially what I'm trying to do here is I'm trying to use one of these charts to make what I'm looking for possible to find. Okay, so let me turn my calculator off. Sorry about that. But basically, yeah, as we come in here, I search normal distribution, and I'm going to be looking kind of at this one, right? We looked back at our distribution here. It's the opposite direction, but we're just going to look at this, and we're going to be able to find it. So what we want to do is we want to look and say, okay, our z variable is essentially going to equal mu minus x divided by sigma minus this, sigma divided by the square root of n. Okay, so here, if we come back to our reference handbook, right, this is kind of what we're looking at here. It's like our x bar minus mu, and you can, I've written it slightly differently, but your mean minus your the hypothesized mean over the sample mean. Let's just come back here and plug in and see where we get. So basically what we're going to have here is we're going to have the 4,400 minus the value that we actually got, 4,000, divided by our sigma, our standard deviation, our population, over the square root of 1. So what do we get? We essentially end up with 400 over 200, or 2. So that's our z variable. What we want to do next is we want to come back to our tables here and say if we come down to a z variable of 2, okay, that variable 2 tells us that 97.7% of the time, 97.7% of the time, we're going to be, on this side of the curve, which is essentially what we're looking for. We're looking for all that area of the curve, and if we look it up, we're gonna find that here. Or we could do it this way as well, and we could do 1 minus this 0.00 or 0.228. So these kind of go hand in hand, but essentially what that means is 98% of the time, okay, 98% of the time, we're going to be good. Okay, hopefully that makes a little bit of sense. If you have questions, pop them in the box. But this is kind of using that z table to understand how to find percentages of normal distributions. There are calculators online that you can do this with, but hopefully this kind of helps as well. Okay, let's keep coming. 2 more questions, then we will call it a night and come back next week for some statics, which is one of my favorites. But what we have here is we have points below can be modeled using a best fit linear regression model. So what this means is, again, we have like an XY plane, we got some points here. I'm not plotting those points exactly, but we can put a straight line through those, and basically we're going to get some model that says kind of y equals ax plus b. Right, and what we want to do is find that. We can go through and find that by hand, but why would you? That's what Excel is for, okay? That's what your calculator is for. So I'm going to bring up my calculator again, and I'm going to come back in here, and I'm going to go to my data. I'm actually going to come back here and go to data. Second data. And where am I? Actually, no, I'm sorry. I'm just going to go to data. I'm going to clear data. Where am I going? Sorry. Oh, there we go. Data. Clear list 1. Sorry. So if I hit data twice, I can clear list 1, and I can start over. So now I'm just going to put in my x variables. 2, enter. 4, enter. 5, enter. 8, enter. I'm going to come up to list 2. I'm going to come in and I'm going to say 2, enter. 5, enter. 12, enter, and 16, enter. Okay, so there are ways to do linear regression, but why? Why? What we can do now is we can come up with our one variable statistics. Actually, not our one variable statistics. I'm sorry. Now, if I go to second quit, I can come to second quit. Let me get out of here. I can go to second stat, right? Statistics. Where am I missing it? Oh yeah, sorry, I just have to come down further. I can do linear regression ax plus b. So if I go to my second stat or second data, I can do my linear regression, and this tells me list 1, list 2. List 1 is my x, list 2 is my y data. I can keep going down, hit calculate, and I get a is 2.44 and b is minus 2.84. So I get this equation of y equals, let me turn the calculator off here, but y equals a was 2.44 x minus 2.84. So now we have an equation. We can plug in a value of 10 to x. Y equals 2.44 times 10 minus 2.84, and y equals, what's this, 24.4 minus 2.84. And if we do that on the calculator, 24.4 minus 2.84 is going to give us about, well, actually it gives us exactly 21.56. This one's kind of in between here, but what we're going to get is, did I type something in wrong? Let me just double check here. Are you guys getting the same thing? I'm just double checking because in my notes I have a little bit different, but let's double check here. 2.44 minus 2.84, 2.44 times 10 minus 2.84. I just want to make sure I give the right answer here. 21.56, that's what I'm getting here. Honestly, I had a slightly different answer in my notes, but I think this is going to be the correct answer at this point, unless you guys got something else. Okay. So that's what we're gonna go with. I'll double check it in Excel, but it's all good. So I mean, we could double check it by hand and but we'd have to find the mean. We'd have to subtract variances from the mean, and it's just, this is one of those questions you don't want to waste time on doing that in the test. Honestly, in 99% of the time you're gonna do linear regression, you're gonna put all your points in Excel and do it in Excel. Actually, I have that Excel spreadsheet. I think I already did. So where is it? Let me pull it up. Why not? This is something where it's like, it's already there. Let's just take a look at it. So did I put the points in correctly? 2, 4, 5, 8, 2, 5, 12, 16, 2.44x minus 2.84, and I got different numbers in here. So 2.44 minus 2.84, and we get that value 21.6. Okay, good. So I'm happy now, and it works. Okay. So linear regression, and hopefully you got that. So no other questions. We're just gonna keep going here. Statistics. Oh man, binomial distributions. And binomial distributions are they seem like they should be so simple, and sometimes I just feel like they're more complicated than they need to be. But binomial distributions are one of those things that I think will probably show up at some point. Maybe it won't. I don't know. Maybe if you've taken the test before, you can let me know what you think. But binomial distributions are kind of the standard distribution. It's like, okay, I've rolled a dice so many times. In this case, I have 3 marbles versus 2 marbles, and if I pick, how many of the times am I going to get? This question basically says I have 5 marbles in a bag. 3 of them are blue, 2 of them are red, and if I pick 5 times, so I pick one, look at it, put it back, pick another one, look at it, put it back, pick another one, so I do that 5 times. The probability of it obtaining at least 4 blue marbles is most nearly. So basically what I'm looking at, I'm trying to find what's the probability that I get 4 marbles that are blue. You know, 4 blue marbles. I probably should have written it that way. I'm going to write it that way. So 4 blue marbles or 5 blue marbles. Okay, so that's the probability that we're trying to find. We know that the probability of getting a blue marble is 3 out of 5. The probability of getting what's left, a red marble, is 2 out of 5. So it's not just a matter of figuring out all the different like scenarios and figuring out, well, okay, how many of them are blue and how many of them are red. I mean, you could take a look at that, but you get the wrong answer. So what we have to do is we kind of have to use a binomial distribution. The binomial distribution kind of says, well, the probability of some value of x is going to equal n factorial divided by x factorial times n minus x factorial times p to the x and q to the n minus x. I mean, that's, wow, that's a lot. Okay, you're probably copying that down. I'm just going to skip over here to the reference handbook for a second because I want to show you where that shows up in the reference handbook. This is, you know, we have binomials. Actually, let me just search it here because I'd like to bring it up here. This is cumulative binomial. I'm going to come back to that in a minute. Honestly, this is the easiest way to do it. But if I come back to, I think it's page 72. Let me just double check here. Is that right? No, it's not. I was looking this up earlier, but let's take a look. I'm just going to keep going to binomials. Here we have this binomial equation that I kind of showed you. And we can go through and solve that binomial equation. But like I said, the easiest way to do this is going to sort of use this chart, right? This chart tells us a binomial distribution. Page 66 of the, is this the other place? Okay, here it is. Yeah, so I just didn't search long enough. But similar equation, the same equation I think I wrote down here. Sometimes trying to figure out how to use this equation on a test is going to be a pain. But this is where, if I come back to, I think, page 80, this is where the binomial probabilities is going to make life kind of a little bit quicker. So you can go through and you can, you know, plug and chug this equation a couple times and it'll work. It'll get you a value. You can also, if you know that binomial distributions, what a binomial distribution is, you can use this table. And the thing is, I didn't use the keyword, there's no binomial in this problem. Binomial. There's no binomial in this problem, but you have to recognize it's kind of this either or, right? The binomial is kind of this either or. Either you roll an odd number or an even number. You flip a head, you flip a coin. You pick a red marble, you pick a blue marble, and there's a probability of success and a probability of failure. So that's a binomial distribution. If you can recognize those, you can come back and actually make your life easier by using something like this. So what does this say? This is the probability that x is going to be less than or equal to x. So let's come back here and take a look for a second. We said, but we want 4 or more blue marbles, right? So we want 4 or 5 blue marbles. That means we need 1, 2, or actually, how many red marbles does that mean? So that means if there's too much to think about. We want to look at kind of reverses here a little bit. Instead of saying, what's the probability 4 or more, we get to look at the probability of 3 or less and subtract it from 1. Does that make sense? So if we, instead of getting 4 or more, our table gives us x or less. So let's find 3 or less and subtract it from 1. So essentially what we're going to say is 1 minus the probability of 3 or fewer blue. Does that make sense? So that's the way we're going to use this. So we've already kind of looked at it a little bit, but what we're going to say here is we're going to say, well, we know the probability of blue is 0.6. We know we have 5 trials, that's our n. And we're looking at 3 blues. So when I come over here, I get 0.6, I get 0.663. Okay, the probability that 3 or fewer blues is 0.66. So we're going to have 1 minus 0.6630. And that's going to be giving us our essentially 0.66 you know, 34 something percent. 1 minus 0.6630 is going to be like 0.337. So it's using a table. I mean, we could go through and let me write this out. Just we've got another minute. I mean, we've got all night, you know. But let me write this out. We could also say this is the table. You know, we just did the table way. We could also do the math way, right? The math way is going to be, say, well, what's the probability that you get 4 blues, right? The way that would write out is like this. We're going to use this. We're going to just solve this equation here for a second. So let's solve this equation. The probability that we get 4 blues is going to say, well, we have 5 trials, so 5 factorial, divided by the probability, or the success, which is going to be 4 factorial, times what? 5 trials minus 4 successes factorial, times the probability of success, which is 0.6 to the 4, okay, and then times the probability of failure, 0.4 to the 1. So when we do that out, I think I get like almost 26%. And then if we do P5, it's something similar. The trials is on top, the success 5 factorial, 5 minus 5 factorial, and you might be looking at 5 minus 5, that's 0 factorial. Uh-oh, did we do something wrong? No, because 0 factorial is what? It's 1. Okay, 0 factorial is 1. So this is 0.6 to the 5 and 0.4 to the 0. Again, 0.4 to the 0 is 1. So this is going to give us, I lost my sheet of notes, but this is going to give us about 8%. So when we add those together, we get 34%. So you can check the math out here. When I did it, it did work out, but you can do the table way, you can do the math way. But if you can recognize a binomial distribution, that's one of the most basic distributions. You've been learning about it with rolling dice, with you know, flipping cards in a deck, that type of thing. But it's kind of an either or. Either you get this or that. And if you can recognize that distribution and use the right graph, you know, that's one of the most basic, I'd say, fundamental types of statistics that you might get into on the FE. So, hey, this is, you know, a long, probably one of the longer sessions that we'll do, okay? In the future, they'll probably be broken up into slightly smaller chunks. We probably won't go past 2 hours, but I appreciate you hanging on here, and I hope this is helpful to you. I mean, like, honestly, I appreciate all the comments and the feedback as you've been going. It's neat to see people from all over the world, you know, from California to Calgary, I mean, coming in, and even here in upstate New York, to work on these problems together. So I hope this helps, whether you're watching live or in the future, you know, you come back to it. But I will repost these problems with a couple of those corrections that I noticed in there, like I missed a couple of the K's, and so, well, you know, those duplicate values. So when I repost things, I might, you know, add a version here and tell you what changes. But if you have any questions, definitely feel free to reach out to me, and I will do my best to get you some answers. But until next time, hey, thanks so much. Next week we'll be on statics and strength. Actually, next week we'll be on statics. But until then, keep working hard, moving onward and upward. And for those of you that want to joke before you leave, I spent a summer in Guatemala doing some engineering work. It was really fun. In Guatemala, there's a Mayan population. The Mayans were actually responsible for creating the number 0 in like the 3rd century BC. So before the 3rd century, the number 0 in math didn't exist. But you know what? I said to them, "Thanks for nothing." Get it? It's too late. Hey, keep working hard. Moving onward and upward. See you next time.